All right, let's dive right into this explainer. Today, we're exploring a pretty fascinating evolution that's happening right now in modern education. For decades, the traditional science classroom has been completely obsessed with one thing, and that's the final product. Getting the right answer, executing the perfect experiment, formatting that flawless data set. But today, we're looking at a radical shift. We're going to examine how science education is shifting its focus away from just creating those perfect final products and moving toward actually building better, more adaptable humans.
So, think about this. What actually happens when biology, computer science, and design tech collide? This question is really the heartbeat of our journey today. Because traditionally, a student studies biology in one room, computer science in another, and design tech way down the hall. But when you force those disciplines to intersect, well, students are pushed completely out of their comfortable, isolated academic silos. They're thrown into the messy, unpredictable, and ultimately transformative real world, where problems just don't fit neatly into a single textbook.
Here is the roadmap for our explainer today. We'll follow the learner's journey through 4 stages. 1. Science beyond the classroom. 2. Local action, global impact. 3. The power of process. And 4. Reflecting on personal growth.
Okay, let's kick things off with Section 1, Science Beyond the Classroom, Breaking Down the Silos.
You know those awful group projects where everyone just divides up the work on day one and barely speaks to one another until it's due? Yeah, this is the exact opposite of that. The Collaborative Sciences Project, or CSP, is a deliberate collision. It requires high school students in the IB diploma program to form truly interdisciplinary teams. They have to point their completely different scientific lenses at a single, complex, real-world issue, relying on the scientific method as their shared language.
And when you combine diverse disciplines like this, the scope of the collaboration is just massive. You've got traditional sciences like physics mixed right alongside design technology. Just picture a hardcore computer scientist trying to explain a machine learning pipeline to a biologist, right? There's inevitably going to be some miscommunication, some confusion, and definitely some frustration. But that messy friction is exactly where the profound learning happens. They literally have to learn how to communicate across disciplines to find a shared solution.
Now here's the kicker. 10. They have to do all of this under a strict time constraint of just 10 hours. Think about that for a second. It takes a minimum of just 10 dedicated hours of focused, interdisciplinary collaboration to completely spark a massive shift in a student's collaborative abilities and their entire worldview.
Moving right along to Section 2, Local Action, Global Impact, the Real-World Crucible.
So how do we anchor massive, terrifying global crises into something high schoolers can actually wrap their heads around? That's the core philosophy here. Students might look at the UN's Sustainable Development Goals, like climate change or public health, and realize, okay, we can't solve that globally in 10 hours. But they can measure air pollution right on their own school grounds. They can identify specific waste sources on a local beach. They're taking abstract issues of global significance and making them highly local, measurable, and actionable.
Just look at what these student teams are actually doing out in the wild. We're talking about biology and physics students modeling vaccine hesitancy to address global health. We've got computer science and environmental students building live sensor dashboards for air pollution using machine learning pipelines. By tackling these highly specific local issues, the expectation isn't that they magically cure climate change over a weekend, but they are absolutely expected to evolve into problem-solving, global citizens who know how to take that crucial first step.
Which brings us to Section 3, the power of process, developing the skills of survival.
Look, working collaboratively under pressure with a bunch of different personalities requires some incredible self-awareness. The whole process actively nurtures the attributes of a globally minded citizen, what's known in this curriculum as the IB learner profile. It stops being just about getting the data right and starts being about being an inquirer, a thinker, a communicator. It's about acting with integrity and genuinely showing empathy towards your teammates when things inevitably go sideways. Furthermore, every single scientific discipline brings a unique survival skill to the team. If you're the computer scientist, you are practicing intense resilience and persistence when you're up late debugging code. If you're from design technology, your job is to inject empathy-driven research and active listening into the group so the solution actually helps humans. Environmental system students bring that crucial interdisciplinary perspective, while biology and physics students really flex their creativity when facing unfamiliar variables. It proves that the actual underlying goal here is building a better, more well-rounded human being.
Looking at this checklist of what makes the project successful, there is a really clear divide between what's essential and what's just desirable. Lasting 10 hours? Essential. Focusing on the process over the product? Absolutely non-negotiable. Linking it to other curriculum requirements like the Theory of Knowledge course or community service hours? That's a great bonus, sure, but the non-negotiable core is the collaborative journey itself. The journey of working together matters so much more than the final destination.
Finally, we hit Section 4, Reflecting on Personal Growth, the ultimate proof of transformation. So you survived this intensive, messy, incredibly challenging project. Now what? Well, every single student is required to write a mandatory reflection on their experience. But there is a massive catch. You only get 100 words, total.
Why just 100 words? Because as anyone who has ever tried to draft a super concise email knows, strict brevity is agonizing. It forces profound self-awareness. Students literally don't have the space to just list out their daily tasks or summarize their data. The most valuable reflections end up being these genuine commentaries on how the students actually felt and how they benefited from the collaboration. It turns what could easily be a boring administrative chore into a mirror, a place where students finally recognize their own personal growth and pinpoint the unique skills they brought to their team.
At the end of the day, this entire collaborative process feeds directly into one very powerful mission: to develop inquiring, knowledgeable, and caring young people who actually help create a better world. It proves that the future of science doesn't just rely on raw data and algorithms, it absolutely depends on compassion, respect, and teamwork. So I want to leave you with this question. You might not be a high school science student, but we all face complex problems every day. I challenge you to embrace the messy process of collaboration in your own life. Focus on the process over the product. Reach out across your own silos and let the friction of working with others spark your own personal growth. Thanks so much for joining me on this explainer, and keep learning.